Okay, well, so welcome to office hours. What's your question?
So I know class was canceled a few days ago, this last Thursday. Wanted to just double check. What are we planning to do on Tuesday?
We will
We
do what we would have done Thursday, which is starting chapter two. It'll be section. Well, actually, we started chapter two, right? We did
Mhm.
chapter 2.1. We will look at if-then statements, about, conditional statements, and I believe that's chapter 2.2.
Gotcha. Okay, that's good.
And I'll make that adjustment to the reading page. I really, this is actually the first time I have sat down at my computer all weekend.
Oh wow, good for you.
Well,
Unless it's been because are you still
yeah,
feeling sick from the other day?
I'm just really tired, just extremely tired. So,
Mm,
but hey, uh, I don't need to harp on that too long here on the recording. I
sure.
plan to be,
Yeah.
in class this week as usual.
Good. I'm glad to hear it.
So
So,
do you want a sneak preview of anything, or were you just wondering, what we're gonna, start on next week? Because I can,
um, it would actually be helpful. To me to talk a little bit about conditionals and biconditionals. I think is really the thing that I am still trying to kind of get my head around. Um,
yeah,
the so I read through the chapter, right? Read through to the end of 2.2, I think,
good.
and it sensible. All makes sense. The thing that I am struggling with though is getting a good like intuition for
Mm,
thinking about only if
right.
conditions, right? It's not clear to me, for instance, looking at page 59 in the book, where it's kind of introduced. P only if Q means if not Q, then not P, right? Or equivalently, if P, then Q. Um, I guess the it's maybe a linguistic problem. I'm not sure. So I
It
wonder if you
is.
could help me
That's
kind of like
exactly what it is. It is a linguistic issue. Let's just look first at the conditional just to be thorough. So, I mean, there are a lot of ways to write it, but one of the ways to write it is simply if P, then Q, where we understand that P and Q represent statements.
mhm,
And the interesting thing about this is there are so many ways to say this. Okay. So the notation, if P, then Q, goes like this, P arrow toward Q. And we read this, if P, then Q
mhm,
generally, or we read it P implies Q. But the intuition behind it is simply this. If the conditional is true and the hypothesis, which is P, is true. Look, I can't even spell hypothesis. It's not firing on all cylinders at all. Hypothesis. If the hypothesis is true and the implication or conditional, it's called both, is true, then the conclusion must follow.
mhm,
So P implies Q could be written something like this. P is true only if Q actually follows. So P can be true only if it actually forced Q.
mhm.
So, um, so if P then Q is the same thing, it means the same thing as P only if Q. Whereas the biconditional, oh, and there are a couple of other phrases too. And there is an if P then Q document that's posted in the good stuff
Uh-huh.
column. folder, and I hope that that helps. At least put in all in one place, all the many different kinds of things that go along with this idea. But one thing to think about is, well, P being true is sufficient to force Q to be true, or P's truth is sufficient to guarantee the truth of Q. So
Mm-hmm.
P is sufficient for Q. Knowing P is true is sufficient for us to conclude that Q is true as long as this implication is true. But
Uh-huh. Right.
that also means Q is necessary for P. In other words, Q necessary for P. Q must necessarily follow P. Because if P is true, it forces Q to be true. So Q is a necessary condition for P to have been true. And it's kind of interesting when we look at the biconditional, which is the if and only if.
Mm-hmm.
Well, that's just shorthand for a slightly more involved statement with the same, meaning, of course, because it's just shorthand. P if Q and P only if Q. It's the same thing as saying that the implication, if P then Q, is true, and its converse, if Q then P, is also true. So notationally, P if Q, that means P will be true if Q is true, is Q implies P. And P is true only if Q follows, is P implies Q. So technically, the actual symbolic definition of P, if and only if Q,
Mm-hmm.
is both P implies Q and its converse, or P implies Q and its converse. Of course, the order doesn't matter here, but I'm writing them in this order because I'm trying to kind of match up the P is true if Q is true part, component with the Q implies P, Q arrow toward P, and the P only if. I'm trying to kind of match that up visually
Mm-hmm.
with if P then Q.
One of the things that you said kind of in the middle there, that um, I feel like I'm sort of just at the cusp of kind of grokking is the bit Q is necessary for P, right? So I'm looking at 61, I guess, right? This is where we've got sufficient necessary conditions.
That's right, because
Um,
you've
can you help me
heard of,
understand
you've certainly
the
heard of
this one?
that. Yeah, go ahead.
Yeah, I was just gonna say, like, can you help me, like, I mean, maybe this is just like a matter of like munging around all these various like ways of expressing it linguistically and showing to myself that they're equivalent to these
Mm,
like formal ways.
mm.
Um,
Would
um,
you like an example?
sure, yeah, that would help.
So here's a nice little mathy example, and it's simply the definition of absolute value applied to real numbers that are in the unit between 0 and 1.
Hmm,
And it turns out that, uh, 0 is less than or equal to X is less than or equal to 1. That's a statement. That could be P, for example.
mhm,
It's a compound statement, but it's still a statement. Okay. If and only if the absolute value of X is less than 1. In other words, X is some kind of fraction that's got a magnitude that's less than 1. So, did I say 0 less than or equal to? What did I mean to put here? I meant to put -1 here. Okay, so it just means that well, it's also true for between 0 and 1, but it's not an if and only if. If I want an if and only if, I have to look at all the real numbers between 1 and -1, and I'll include the endpoints. We didn't have to make an if and only if true statement. We could have made these strict inequalities, and we could have made this a strict inequality. It would still be a true if and only if statement.
Mhm,
But the bottom line is, any real number whose distance from 0 is less than or equal to 1 is a real number whose value is between -1 and 1. So this is a true if and only if statement. This would be our Q part.
mhm, mhm,
I mean, this forces that, and by definition of absolute value and what we understand about real numbers, this forces that as well.
mhm. I guess taking an example, negative zero point 0.5.
Yeah.
Negative zero point 0.5 would be a valid value for x in P because it is greater than or equal to -1, and it is also less than or equal to 1. I'm satisfied there.
Yes. This,
And the
that, right.
negative,
This is a predicate. I called this a statement. It's actually a predicate statement. We often use those two terms interchangeably. But
hmm,
yes, this becomes true if we pick, for example, this value for X. It makes both P and Q true. Yes,
mhm,
that's a good example. Because, you're playing games, not just with, a fraction that's between 0 and 1, but you've picked a -1, in fact. And that's a nice -0.5. Yeah. Maybe I should write that a little bit better. Oops.
so can you help
Go
me
ahead.
see how do we map, for instance, like this example or another one that's similar to uh, the language like Q is this hold on, my thing's in the way. Q is necessary for P
Right.
up above.
Right. Right. So the way we would phrase this sort of uh, nicely, okay, excuse me, I mean to be pointing to this.
Mm,
It would be that P is necessary and sufficient for Q. And it's called necessary and sufficient conditions. It's a very, very important and popular game for mathematicians and logicians to play the necessary and sufficient game. Because what it means is if we state P, we are talking about the same, structure or statement that we're talking about when we state Q. But the application is generally something kind of interesting. For example, maybe in out the world of algebra,
mhm,
something is happening, something true is happening. And we've got some statement P over here in the world of algebra. Whereas, here perhaps, in the world of analysis or topology or, geometry, there is a structure that has properties basically that are the same properties as Q, but just in a different world with different language. And this is one of the main applications of necessary and sufficient conditions is you discover something that's true in the world of, say, algebra or homological algebra, then you're looking for parallels in another part of mathematics. And when you stumble upon a structure that lives in this other world, sort of in the same way, with the same roles that the structure described with the statement P in the algebra world, then we make a comparison between these two statements involving usually quite, what look like different objects and different definitions. But in fact, if there's an if and only if situation, it means that whatever's happening here in the world of algebra is mirrored in the world of analysis. It's one of kind of the biggest and most important deals in mathematics is to try to draw parallels in order, but in between fields in order to get a better understanding or to get access to tools that exist in one of the areas of mathematics,
Mhm.
map the statement P, which maybe we don't really understand very well in the world, say, of algebra, over to its corresponding structure in Q, say in the world of analysis or, whatever, set theory or, topology or something, metric spaces, then the tools that can come to bear on the objects that are described in statement Q can be applied to those objects. The hope being that those tools can then allow us to map other statements back into the world of algebra that would have been difficult to prove using standard rules for
Mm.
algebra. Does that make sense?
Mhm.
Yeah, and this is exactly what happened for, you've heard of Andrew Wiles and the Fermat's, famous last theorem
Mm. Mhm.
that talks about solutions to x to the n plus y to the n equals z to the n. And those that proof was hard to get to without mapping out of pure algebra, x to the n plus y to the n equals z to the n, without mapping into the world of elliptic curves, where there were tools in the world of elliptic curves that allowed the final attack and conquering of that question back into algebra.
Mm. I actually haven't heard of this guy. What's his first name? Wiles?
Andrew Wiles. Yeah.
Andrew Wiles.
Was he at
So
Cambridge or
somebody
Oxford?
somebody did it.
Yeah. Yeah. He solved Fermat's last
Well,
theorem.
I'm gonna
And
Google this.
it was a really one of these kind of fairy tale stories, ivory tower stories. He literally worked quietly for 20 something years up, in his attic, and his wife brought him tea and biscuits, and because he was afraid to present it until it was finished. He did stand on the shoulders of numerous people who had gotten uh, kind of core results in elliptic curve, um, the field of elliptic curves. But he
Mm.
just went further than they had been able to. People had been, of course, working on the problem for ever. Um, yeah,
Mm.
Andrew Wiles. Yeah.
No, I mean, the one of the examples you brought up in class the other day, I mean, this is a much more pedestrian example, but like going between like magnitude and multitude, or between algebra and geometry, right? You were bringing up like Descartes the other day.
Right.
There's all sorts of nice things that are easier to prove using sort of like elementary school geometry. Um,
Exactly.
than they are algebraically. And conversely, I guess like, there's lots of stuff that's easier to do,
Hello.
have in your bag of tricks
Right.
geometrically.
Right, right, and it's a really important process for mathematicians. And I'll give you an example from my own life in research. We, um, I say we, my advisor built a new mechanism for generating a formal language. Find out automata, build very particular classes of uh, formal languages, and then if you have say a push down automata, you can get a larger, more general class of formal languages using that as your generative mechanism. And one of the things we were trying to do was really get a handle on what is in the test tube at equilibrium if we follow strict biological rules. And it turned out that without using strict biological rules, the world of splicing systems is uh, NP complete.
Mm,
But if you start to impose the strict symmetry that you have when, say, an enzyme, sees a sequence and cuts, with a sequence specific kind of cutting. And when you impose those rules of symmetry and reflexivity and transitivity, then the world of languages is actually much, much smaller. And to some extent, it's
Hmm.
still, even now, an open question exactly which languages one can get with splicing. I mean, that's just an example I happen to be familiar with.
Hmm. Are we going to work on formal languages? I
Mhm.
think this is in, I'm looking through the table of contents. This is like chapter 12 kind of territory.
Yeah, it's not in the scope of this course. There was a theoretical computer science course
Hmm.
being offered upstairs there, and the guy that taught it, gosh, I'm trying to remember his name, Zamond, was it Zamond, is no longer there. And they
Oh, I
haven't
see.
taught that in a while. I would love to teach that course because thinking about, generating sequences of strings and asking, what kinds of, you know, predicate syntactic depth is required to build that class, say, of languages, versus, the kinds of little machines that are applied like automata to build these languages. Uh, it's a really interesting, it's a really interesting and fun puzzle.
Mhm. Yeah, it seems like well, yeah, it seems like fun stuff.
Yeah, grammars are fun.
Are we planning on going through chap I'm sure this is just in like the syllabus and you'd be justified in telling me, well, go look, it's on
Oh, no, no. What are we
let's see.
going to do that is not maybe offered in other courses, other sections? I say other courses. Other instructors uh, probably will not hit circuit design, but we will do some circuit design because I think it's fun and it gives
Hmm,
us an opportunity to see how playing with zeros and ones moves from being just a game of logic. If you and together a one and an O, the output is an O because one is true and O is false. And
mhm,
having, both is what's required to have the and operated statement be true. Um, but the rubber meets the road when you try to use and gates and or gates and not gates to then build a machine that actually does something real with the digits, which
mhm,
on the one hand represent true and false, but on the other hand can actually represent binary numbers. And one of the things that we can build with a circuit is an adder that correctly adds binary digits. And I think that's important. I think it's interesting for computer science students to see that. So
uh-huh.
we will look at some of that. But
It's fun.
otherwise,
Yeah, this is
what?
like
Yeah,
chapter two. Yeah, chapter two. Wow. We're
yeah,
gonna
it
do
is.
some of this soon,
It's
yeah?
2.5. It's 2.4. I think it starts in 2.4 and then 2.5 gets into binary addition and adders, half adders and full adders. So half adders and full adders, I have traditionally hit that up in the past. Uh,
Mhm,
this particular semester, I'm going to reserve that as an if time topic. But certainly
mhm.
we will do circuit design. That'll come right after we finish arguments. Uh, but
Cool.
adders are just, they're just baby circuits that add binary digits and give you the correct output. And I think that's really cool to see how something that seems theoretical actually underpins the mechanical or the electronic, depending upon how you look at it.
I'll see if I can find I'll see if I can find this. I think still remember this was a while ago, a couple years ago, probably. This was like a pandemic sort of rabbit hole, probably. I saw this really nice video where this guy got walked you through like setting up like these kind of baby circuits.
Mm-hmm.
And he went through all sorts of, nice simple things like, building building gates and then starting to like add up to like adders, and I think he built like
Exactly.
memory. Memory was really cool. Like uh, I that was kind of had like my mind blown a little bit by that.
Yeah, I've got a book that you can borrow if you could stop by the office, that talks about sort of like the rudimentary idea of memory, and then once you have a Turing machine, there's a tape, and it's by infinite, and the
Hmm.
machine writes to the tape. It can overwrite. So the tape, just imagine that there's like a little head that
Hmm.
reads and writes to a bi-infinite tape. So here's the tape. And the tape can, move either way. And then this little head can read what's here, either, it's an O or it's a one, and it can do nothing, or it can overwrite it. Maybe there's some O's here, maybe there's ones here. Um, oh, no, no, no. Jonathan has some interests that kind of go beyond the scope of the class. But
Oh,
it is interesting to understand that there is a whole world of computer science that doesn't have to do with programming. It has to do with more theoretical concerns, and that's what we were talking about here.
okay. Thank you.
Uh-huh. But yeah, we were talking about the implication, the if P then Q, and we're going to be discussing that in our next lecture. And here are different ways to say if P then Q, that P implies Q, or P is true only if Q follows as true. And then, of course, we can say if P then Q. But here are a couple of other ways to say if P then Q, that P is sufficient. P being Q is sufficient to force Q to be true if the implication, if P then Q is true. And then Q is necessary for P. In other words, Q must necessarily be true for P to have been true, because if P is true, then it forces Q. So we were discussing the definition, or trying to understand the conditional if P then Q. And then the biconditional goes both ways. When the arrow goes both ways, we read it P if and only if Q, but what it really means is P if Q and P only if Q. And I was just breaking that down for Jonathan, that the P if Q part is the part where Q is enough to force P. In other words, P must be true if Q is true. In other words, Q does imply P, and P is true only if Q follows. That's the same thing as saying if P then Q. So I was just writing down some sort of a sneak preview of our lecture that's going to happen in our next day 3 class.
Okay, because I was watching videos about the subject and I was seeing the arrow. So
Uh-huh.
okay, it's good that we're gonna go over it in class as well.
Yeah, and the if P then Q is a little bit non-intuitive, because you know how we were making truth tables? We'd make a column for P and then make a column for Q, and then we made columns for P and Q. We made columns for P or Q. Remember when we were using truth tables as sort of
Yeah.
a shorthand way to describe the rule? Well, this one is really interesting. Under P, of course, would put true, true, false, false. And under Q, we put true, false, true, false. Well, if P then Q is interesting because it's true. The rule is this will be true most of the time. In fact, it's easier to say when it's not true. It only fails if the hypothesis P is true and the conclusion Q fails to follow. This is the only time if P then Q fails. In all the other rows, if P then Q is true. And the way to think about these two in the third and fourth rows is, hey, if the hypothesis is false, then it doesn't really matter whether Q is true or false. The if then will be true by what we call false hypothesis in these two rows, because if P then Q only tells us what should happen if P is actually true. If P then Q says, hey, if P is true, then Q better follow. It says nothing about what should or should not happen if P isn't true. And in logic, if it's not a lie, then we say it's true. So in rows 3 and 4, where P is false, we say the if-then statement is true by false hypothesis. So that's sort of the most interesting and probably challenging thing for students is understanding intuitively the truth table for if P then Q. It's almost always true. It only fails if the hypothesis was true, but the conclusion failed to follow the way it's supposed to.
Okay, thank you.
You're welcome. Do you have other questions?
Um, Not right now, maybe in class.
Good. If P then Q is very non-intuitive because weird, silly statements can be true. Let's look at an example. It's kind of non-intuitive. So here's one. If Rebecca is 10 feet tall, then the sun is a planet. So let's just break that down and see if we can figure out if it's true or false. It's kind of nice to parse things out, and let's let P be the statement that Rebecca is 10 feet tall. And we can let Q be the statement the sun is a planet. So do you see how this statement breaks down to an if P then Q?
Yeah,
So do you think that this if then statement is true or false? Well, that's where we get to just refer to this little truth table, and let's see if we can figure it out. The truth table for if P then Q says, hey, if P then Q is only going to fail in one situation, and that would be if the hypothesis is true and the conclusion Q is false. In every other situation, right, we put true, true, false, false under P and true, false under Q. In every other, possible way of assorting the truth values of P and Q, if P, then Q is true. And in fact, in particular, when P is false, if P, then Q is true by false hypothesis. And if we're playing set theory games, we say it's true vacuously. So what do you think now?
about whether if it's true or false.
So let's look. What's the truth value of Rebecca is 10 feet tall? Is that true or false?
False.
It's false. What's the statement? The sun is a planet. What's the truth value of that statement?
It's true.
Wait a minute. The sun is a star, not a planet. I'm sorry.
My bad, my bad.
The sun is a star, right? I could have put the Earth as a planet, but the point is it really doesn't matter because the minute that we know that P is false, we know we're looking at either row 3 or row 4, right? Because you're not 10 feet tall.
Yeah.
In either one of those situations, whether the sun is a planet or whether the sun is a star, it doesn't really matter what we wrote here, whether it was true or false. It happens to be false. But the point is, if P then Q is going to be true by false hypothesis. So that's what's so weird is silly sounding statements. If Rebecca is 10 feet tall, then the sun is a planet. Well, that's silly because you're not 10 feet tall, but it happens to be true according to the way we evaluate an if-then statement. So that's kind of the most curious thing about the if-then statement is that no matter how silly the hypothesis is, if the hypothesis is false, the if-then statement will be true.
You mentioned in there, if we're playing set theory games, then it's vacuously true. What's the thing from set theory where we get that from?
Okay, so I'm so glad you asked. Do you remember that we had a fact about subsets, and that is that A is always a subset of itself for any set A, right?
Hmm.
We check subset inclusion by saying, hey, we're going to look at the elements of this set on the left, to see what's whatever elements A has, and we're going to check and make sure they are also elements of the set on the right. Of course, it's A, so the same elements will be there. That's a fact. But there's another fact, and this is the vacuous part. The empty set is a subset of A for any set A. Let's think about why that's true. The set on the left will be a subset of the set on the right if each element of the set on the left is an element of the set, in this case, A on the right. Well, are there any elements in the empty set?
There are not.
There are not. So there is nothing to check. The statement, if X is an element of the empty set, then X is an element of A, and we weren't ready for that until we, talked about if-then statements, but that is
Hmm.
basically the way we check subset inclusion. For any element X in the set on the left, we're trying to answer in the affirmative that that element is an element of the set on the right. In other words, we're trying to confirm this statement for all X, in the universe, whatever the universe is. We're usually told what the universe is. There's some kind of overriding universe where all the elements live.
Hmm.
This is always true
Hmm.
because there is no X in the empty set. So the hypothesis of this if-then is true vacuously because the empty set is a vacuous set. So from a set theory perspective, we say, an if-then with false hypothesis is true vacuously. It stems from this idea.
Hmm. I guess this, I mean, tell me if this seems like my intuition's wrong, but like it seems like this is the type of thing that's like just by convention. There might lead it might lead to some contradiction or something, which would be interesting to see if we said like let's define like the answer to this question. If X is an element of the empty set, then X is an element of A. Okay, sure, grant that. The answer uh, to like, is it an element of the empty set? No, because there are no elements. Um,
And hence the false hypothesis, the vacuous hypothesis.
aha, I see. This maps back to the bit above. Um, by default, I see. Okay.
Right. I mean, yeah, I mean, by false hypothesis is not very elegant. And anyone who studies math studies some basic set theory. So it's just
Hmm,
more elegant to say it's true vacuously. But this, I like to think of this as being the origin of sort of that ilk.
hmm. I think I see it now. Yeah.
Mhm, mhm. It's a good question. But I couldn't put all this into our little set theory special homework because we weren't prepared to talk about an if then. I just tried to kind of intuitively explain, I think, in that special homework that there is nothing to check. There is no X that has to be in A in order for the empty set to be a subset of A. There's no X to check. And so, this is going to be true by false hypothesis.
Hmm, hmm.
So Rebecca, did you have any specific questions about any of the special homework questions that we're looking at to review?
None that comes to mind so far, but I could acts in the future. But
Okay, that's fine. Don't want to, I'm not trying to put anybody on the spot. Well, thank you so much for coming to office hours. Rebecca, do you have any other questions?
no, ma'am.
Okay, I'm so glad that you came. And we will continue to have office hours. And when, we have, exhausted our questions about material that you'll actually be tested on, then we can always talk about, extra things like grammars and little machines that build languages and that sort of thing, or whatever you would like to talk about. But for now, I'm probably going to maybe edit this. Probably going to
Oh,
edit.
to take take some of that
I'm going
out.
to edit this office hour and load it up into the YouTube studio and cut out most of the discussion about grammars and just keep these 2 pages of notes that are pertaining to what you really do need to understand.
That seems reasonable, especially since the first one for the semester, right?
Yeah, I'd like it to be, I don't want to be taking people off and deep dive into the abyss,
Yeah. Thanks for talking about it. Regardless, it's fun stuff.
It is fun
It's
stuff, and I do have a book that you can borrow if you want.
Well, yeah, I'll take you up on that.
Hopcroft and Ullman, it's the Bible for theoretical computer science, with all the pictures of the different little machines and then a correspondence between the languages that can be generated in those machines.
It's yeah, it's cool to see, like, apropos the thing we're kind of like opening the conversation with, like the places where you can draw analogies between these different like fields of math. And it's also fun to see where there are like disanalogies, like this if P then Q, this conditional form, right? Like
Right.
it was really like counterintuitive for
It
me for
is.
a bit, because
It
like
is.
thinking about it in terms of programming, it works very differently than what your intuition is going to be from there.
Right,
You
because
write some function that
right.
does a thing, and
Yeah.
you're working with booleans, and it's just a totally different sort
The
of framework.
application is absolutely different because you're checking the truth of the hypothesis to figure out whether to execute the then clause or whether to execute the else clause, right?
Right.
Yeah.
It was helpful at some point while like working on the homework. I, I was like looking at the truth table of it or something. Um, I just thought like, oh, like this is just another binary operator, uh, like
Right.
and or and so on,
Right.
and it has some truth table. Like thinking of
Right.
it just as like I don't want to say function, but like uh, thinking of it as an operator that will spit out some truth value given two arguments, was helpful for me.
Good. I'm glad to hear it. I'm glad to hear it. Um, yeah, we're building a logical world, and in fact, everything that we build that includes the if then could be built without using if then. Having the and, the or,
Hmm.
and the not is sufficient. But it's fun to play conditional games. And the main motivation is to understand that a major game for mathematicians is to try to say, hey, P and Q are saying the very same thing, but perhaps in completely different worlds. It's incredibly powerful and important for mathematicians to prove statements about necessary and sufficient conditions. It's just a big deal. You always want to be able to do that if possible. Okay. Well, folks, we're going to wrap up our first office hour. Thanks so much for playing. I'll post these notes and I'll trim up this video, and we'll see you in class this week.
Cool. Thanks a bunch.
Thank you.
Thanks so much.